least from the students.
Nice. Should I put this back?
Coleman and Will are much closer. They're not, and Henry. Sorry, Henry. Okay, hold on. Morning meeting. Showing. Constant presence. Sweet. Almost there. Attendance ready to go.
I'll try to zoom this in.
And hey, Jordan's back. Cool.
Yes, hello.
Hey, Jordan.
Okay. Very nicely said.
Is it in the directory?
And
I'm just going through the recent calls.
I'm gonna add it to the directory.
roll down. Here.
You guys want to do yourself right.
Forgot to do that.
It's right. Kira is here today. That's Zoom. This aims at us. Kira is here. She's at school today, but she's running late now. Yeah.
You guys scoot in.
Okay. All right. Let me see here. We've got Coleman and Henry here. We've got Will. Looks like we're missing Eni. And we have a new student with you, Peter, right?
Yeah.
What's your name,
My
sir?
name's Limbo. Limbo.
Limbo? Well, welcome. And I'll just kind of like half edge you to this assignment sheet here. Limbo. Say X, 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 and then here and here. Okay, so we are missing Eni.
Shared his Google Drive with you.
Kira is absent as of right now. Kaylee's here, Jasmine's here, Coleman's here, Will's here, Henry's here, Dallas is here, and Chris from Array is missing, right? Okay. How you guys doing?
Good.
Doing well?
Doing well? Cool.
Mm-hmm.
So, let me see here. Close that off.
Here's Eni.
Couple of people had, a couple of questions on the first half of worksheet one is, plug and chug. A little bit fun to plug things in and see numbers do things, and very slightly different algebra than there's Eni, welcome Eni, than necessarily the examples I gave. Like, I don't think I solved for velocity that many times, and some of the problems I said solve for velocity instead of solving for various times. The second half is actually, mathematically speaking, very easy. You just have to divide lengths by speeds, but you gotta decide the right lengths to divide by. And a few people were still a little bit freaked out by that. Some people had no problem at all. Just in case, I threw up a link onto the assignment sheet this morning with a little bit of advice on ways to think about it. But I also said in that video, and I think in an email or something, that don't think, I am going to grade this homework assignment, but the problem you'll run into with relativity is not being able to plug the numbers into the equation. It's going to be flipping the dilated and undilated, or the contracted and uncontracted values. Those are the errors that you're going to make. And if you just get things backwards, I'll take a tiny little bit of credit off so that you did something wrong. But otherwise, it'll be fine. This isn't a test. It's a communication. It's a moment for me to see if you're getting what I'm talking about. And I kind of want those latter questions to feel a little bit weird, but they're not in the end hard when you do them correctly. I will talk about them in detail next time we meet. But as far as right now is concerned, let me know if you have any more questions, but just try and get that done by the end of the night tonight, okay? Some of you have already gotten it to me, so no problems. Quick show of hands, how many of you have, there we go. How many of you have decided to print and scan? Oh. Okay, so the rest of you guys are doing it on the worksheet using the equation editor thing?
Yeah.
I don't have any materials yet.
Yeah, I have to share with you. Hope Peter, if you can, you just, show him what you have, and Limbo, if you have an email address other than your school email address that you want me to share things to you through Google Drive, email me that. Peter should have my email address. It's btaylor@hopkins.edu. Email me any email addresses that you prefer for me to use. We'll get you all set. Alrighty?
Okay.
Moving on. So, two things I wanted to talk about today before getting into the hardcore stuff. Here, hold on a second. One was the mountain problem that we were talking about last time with the tunnel, and you guys had posed some interesting questions in the very last minutes. And where is that? I'll just reproduce it. It's fine. I'll just insert another drawing. And I gotta share screen. Chrome. Okay, so we have been talking about a train passing through a tunnel at absurd velocities, and we started to talk about the gates snapping shut. Sorry, I'm not making any eye contact right now. I'll be okay. Now, let's say for the sake of argument that the length contraction is such that as we watch this train into the tunnel from our perspective, the train exactly fits inside the tunnel precisely. Okay, and the question comes, if there are gates at either side of the tunnel, here and over here, that shut when either the front of the train is exiting the far side or the back of the train is entering, wouldn't it be true that in the perspective of the person watching from outside, the train would become trapped inside, and to the person on the train, in fact, what would happen is the train would be its normal length, the tunnel itself would be shrunk, and so the front would crash into it before the back ever had gotten a chance to enter. And I think Peter said, well, what if there was just a button? And we were talking about also, like, this could have been like different cans of paint that explode on the ground. And the question is, which one happens first? Does, on this left-hand side over here, if in one reference frame you see this close first, and another reference frame you see this close first, which one is true? Isn't it not okay that they disagree? And the answer is simply this. Simultaneity is destroyed by relativity. The idea that two events could appear to happen at the same time in one reference frame and not at the same time in the other reference frame, the idea that that is possible is weird to you. But that is the case, and you don't even have to be traveling at a velocity for that to occur. You remember in one of my very first videos, we talked about the length of a car, and we said it could be signified by looking at pulses of light coming from either side. And if we were standing, let's say, here in the center of the car, those two pulses of light would head towards us from these two different directions, but they'd travel in the equivalent distance at the same speed, and we'd see the lights blinking at the same time. If, however, we moved all the way over here, you can see obviously those distances are now different, and so the pulses reach us at different times, and the lights, hello Kira, the lights do not appear to be simultaneous anymore. That doesn't mean that in that case that the length of the car had even changed. When we add relativity to the problem, if this thing is moving, simultaneity is ruined by the fact that the light is coming from different positions. And additionally, things are further screwed up because the answer we get is that the object is shrunk in the process. But still, no matter what, it's not required that two different people see the two different events, the gate shutting on either side of this thing or paint being splattered on either side of this thing, as being at the same time. The reason why you think they should feel that is the same is you think of simultaneity as being 0, that the difference in time between the two events is nothing. And so how could 0 experience time dilation? And the problem is that's not a 0. You can't measure the time between events in that way if they're in different locations in space. Where you are relative to them matters, all right? And there is no problem if things are non-simultaneous in one reference frame and simultaneous in a different reference frame. The other thing we were talking about that was kind of cool, just to finish it up, is, and I said this at the very end, but it's worth repeating because some of us weren't here. What happens in the train's reference frame is that the front of the train has come into the tunnel, it gets to the other end, the far gate snaps shut, like that. What does the train do when that gate snaps shut?
Stops. Decelerates.
How?
Oh, yeah.
It exerts a force.
Yeah, a force is exerted on it. There would have to be a completely stupid force. There's huge problems with that. Like an unbelievable amount of force would be necessary. It decelerates. So what happens to the velocity that it sees? Because remember, the train sees the mountain as having, here I can do it this way, sees the mountain as having the velocity. So the train sees the mountain coming at it like this at some large velocity. As it hits the wall, what happens to the velocity of the tunnel as seen by the train?
It decreases to 0.
It decreases to 0. So what happens to, sorry, I keep on looking at the wrong screen and it's hard to move. Okay, there we go. What happens to the length contraction of the tunnel as the velocity decreases?
It contracts less, so it gets longer.
Yeah.
So the people in the train see the tunnel as they smash into the wall and get turned into salsa. No laugh, it's fair. It's fair. They see the tunnel expanding and expanding and expanding. And then finally, they see the gate snap shut on the other side. What's important here is that the person outside saw the two gates snap shut at the same time. The people in the train saw them snap shut at different times. That is okay. What would not be okay is for this person out here to say that the train got trapped, and a person on the train to say that the train didn't get trapped. That is not okay. That is like all of reality is broken. Causality is over. We'll save that for when we do quantum mechanics, when causality will be over. For now, causality still works. And so we have to agree that the train gets trapped. And the thing is, we both agree that the train gets trapped. We just disagree about when. Okay? Any more questions on the tunnel paradox? And I mean, I would imagine there might be some deep ones. There might also be not much. Nothing? Okay. Now quickly on to the relative velocity problems. I will eventually send you a video that is totally your option to watch. It is not assigned. That will go through all of the algebra that takes you to the expression for the two velocities. If you want to see it, you can watch it. But the equation we got was that if we had a spaceship or something traveling forward at a velocity, let's call it u prime. I'll make that bigger. And some projectile were fired from it at the same time. I'll go with no reason. This. such that the people on that spaceship saw it traveling forward at a speed v, and I got to label my frames here. We'll call that K, and we'll call this K prime. Those are tiny. The equation for the velocity of that same object prime, so that seen by the person on Earth, what would you expect it to be back in regular old physics class?
V plus U prime.
You expected it to be v plus u prime, and what did I say about that instinct in the video?
It's wrong, but pretty much right.
Yeah, it's wrong, but it's close, and it's a really good way to remember the equation. Really good way to get started. What's the correction factor?
Over 1 plus v times u prime over c squared.
Okay, cool, we got it. Your next worksheet will have problems on this, and they will be of multiple different kinds. It'll be like, set up exactly like this. It might be that projectile is instead fired from the Earth, and you're asked for what the velocity is as seen from the rocket ship, etc. Those can be maybe even more confusing to tell what reference frame is what when you're solving the problems. In the sample problems, I gave you a set of adages for what each thing v, u prime, and v prime are. Does anybody remember what I said those is a verbal way to think about what each of those things is? Dallas?
You said that v prime was the speed of the thing as seen by you, and that v is the speed of the thing as seen by someone else, and u prime is the speed of the someone else as seen by you.
Yeah, absolutely. V prime is the speed of the thing as seen from where you want to measure it from, where the question is. And in our case, that would be, how does the Earth see it traveling? The answer is, well, how does another reference frame see it traveling? That is this thing here, v. Okay? And how fast is the other reference frame traveling? That is this, u prime. Use the equation properly and you will be safe. And use your old instincts for what it should have been to get started in writing this. So let me change the example somewhat. Let's say that it was a classic problem. A truck is traveling forward at 30 meters per second. I'll fix it. There we go. And a person on that truck throws a can from the window, a terrible litter bug, as that person is, at 10 meters per second relative to him. All right, don't suck. There we go. What would your instinct tell you the answer is for v prime?
40 meters per second.
And that is almost right. 40, and then you would put down here 10 times 30, and it would barely be in effect at all at these speeds, because the 10 times 30, well, that is 300, would be divided by, what is that, like 9,000 trillion? Wouldn't matter at all, but that's right. Now, what if that person threw that can at negative 10 meters per second relative to them? What's your instinct for the answer?
20.
20. Does the equation still work? Yes. This would become 20 up here, and this would become 1 minus. The key there to realize is that the minus sign mattered, right? 30 times negative 10 is negative 300, and that does matter in the equation. Questions there? Nothing? We're good? All right, cool. Okay, so next topic.
Wait. I have a question.
Go.
Okay, so like when you throw the thing. Oh wait, never mind. I don't have a question anymore.
What was it, just so I can know?
Okay, so basically what I was thinking is that when you throw the ball forward, you're gonna get like a smaller velocity than what you normally think it is, right? Because you're dividing by a number greater than 1 at the end of the day. But here you're dividing by a number less than 1, so it's actually going to be a greater velocity than what you think it is. And that kind of didn't make sense to me because I'm thinking like, shouldn't it still also like, I don't know.
Yeah.
It just didn't sit well with
And
me.
the answer is no. And it's because the two of you were measuring all of those lengths in different ways.
Yeah.
And what this equation is actually saying is that the person in K sees the ball travel 10 meters backwards in a second. But that distance traveled is outside of the spaceship, right?
Yeah.
So it's length contracted. So the people standing outside don't experience the same length contraction, and they see the same event as having occurred over a larger span of distance, and they see a larger velocity. And it all depends on the orientation, and the equation means what it says. But yeah, I agree with you. It is weird. And actually, in my last example problem, I never used numbers like that for an example problem before, and it's dramatic. It was something where the Enterprise flies past Earth at 0.9 C. The Earth fires a rocket at it at 0.99 C. You would expect the people on the Enterprise to see it coming at them at 0.09, quite slowly, and the answer is like 0.82. Like the thing is going way too fast. And just wait it. Okay.
I had a question too.
Yep.
Can the sum of v and u prime be greater than the speed of light?
They cannot. Mathematically, the sum of v plus u prime can be greater than z, right? But if the question is, can the second velocity, can v prime be greater than c? The answer is no. There's a couple of things at play there. In my original equation, vu prime, the first thing that's at play is that we're never inputting any values for v or u prime that are bigger than c in the first place. And so as a consequence, the way that this math works out, since v and u prime are always less than or equal to c, this fraction will never make a number bigger than c, or even equal to c. Well, except for in one case. So yeah, if you put that v were equal to, 78 times the speed of light, and you put in that u prime were, 36.5 times the speed of light, yeah, fine, you would get, well, actually, I haven't tested it, but you might get a velocity larger than the speed of light, but you can't do that. Now, your question is a good one though, because I have not yet given you any evidence as to why it is that I can't do that in the first place. Right? I've given you no actual evidence as to why we can't go faster than c. No physical reason, and that's coming up over the weekend into next week. When we look at relativistic momentum, what we will find is that an object traveling at c with mass will have infinite momentum, and will have infinite kinetic energy, which would mean it took an infinite amount of work. It also will mean that it will have an infinite mass, so that it is a black hole that would consume the entire universe, and if it were possible, we all would have been dead many, 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 many years ago. Since we're not, velocities stay below c, but we'll see that all eventually. Good questions. Any other questions?
2 yeah. 1 plus 1, yeah.
Nada? Nothing? Okay, moving on. had that open. I guess I'll have to do it again. So much stuff. Okay. Cool. I would like to decompress a little bit on some reading stuff. And, I understand reading translated German, not always the best experience. Reading translated German by Einstein about relativistic physics, really not always the greatest experience. So here's what I have gotten from this reading, and I just wanted to share it with you. On the in the document, if you wanted to look on your own, but I'm going to pull it up on the screen here. I am going to the 24th page in the PDF, which is page 1 of the actual book. And by the way, you will enjoy the next reading we do from Feynman a lot more, I think. So, starting here, physical meaning of geometrical propositions, and I can't help but read out loud some of this. In your school days, most of you who read this book made acquaintance with the noble building of Euclid's geometry, and you remember, perhaps with more respect than love, the magnificent structure on the lofty staircase of which you were chased about for uncounted hours by conscientious teachers. By reason of your past experience, you would certainly regard everyone with disdain who should pronounce even the most out-of-the-way proposition of this science to be untrue. But perhaps this feeling of proud certainty would leave you immediately if someone were to ask you, what then? Do you mean by the assertion that these propositions are true? Let us proceed to give the question a little consideration. Thoughts, including, if it's like, I thought that was really pretty, or it's, I really hate Einstein, like whatever it is. It's fine. What are your thoughts?
Really hard to understand.
I like a lot of
it is hard to understand. It's true. It's worse than Shakespeare by far, but to me, at least. And I'm a physicist. Go ahead, Jasmine. What are you going to say?
Oh, I always say I kind of like it. Like all of the weird adjectives, like all like the great, very extreme adjectives and metaphors.
And the huge run-on sentences and the...
Yeah.
Yeah. German's a very different language. That's part of it, but hard to understand. Any other comments? Yeah, Will. Oh, you're muted. You're muted.
There we go. I like how in-depth he goes with things that we accept as facts now, like how to measure something with a ruler.
Good for you.
How neat that is.
Yeah. I gave you a little bit of a preface there to warn you, like, hey, he's going to do this for a reason. Like, he's going to break this stuff down. And so if I just gave it to you blind, you probably would have felt a little more like, why bother saying any of this? But we'll look at that a little more deeply in a minute. Other things? Anything else? Siri, do you have anything to say? No. Any comments on content? What is he talking about in this paragraph? There's only, I could say in 2 words, including a famous person's name, what he's talking about.
Euclid's geometry.
Euclidean geometry. And he's basically saying, you guys, you love Euclid. You think he's the best. You think squares are 4 right angles with the same length in between each of the turns. You think circles have a circumference equal to 2 pi r. Isn't that adorable? You're so cute for thinking that. That's so, sweet. Euclid's geometry will prove if you, I don't know, maybe you got it, but like for me, like the 74th time I read this, I understood that his real thing is to be like, here is what you hold most dear, Euclid's geometry. This is the thing that's wrong. Not the laws of physics and not the constancy of the speed of light. Euclid is wrong. So he starts immediately with that for a reason. he talks about points and straight lines and stuff like that, and starts to really, as Will said, very carefully define everything in a way that is tedious. And I'm surprised the book survived as long as it did without physicists to read it. I'm next going to go to page 6, which is into, I think, a chapter or two later. It's page 29 in the document itself. Unless somebody has something that they wanted to talk about in that early chapter. Oftentimes they're like, I don't know, I made it through it. But is it okay if I move on? Does anybody else have anything else to say? Okay. In this area, he starts talking about Trafalgar Square, London. And then the primitive method of place specification deals only with places on the surface of rigid bodies and is dependent upon the existence of points on this surface which are distinguishable from each other. But we can free ourselves from both of these limitations without altering the nature of our specification of position. If, for instance, and here's the key part, a cloud is hovering over Trafalgar Square, then we can determine its position relative to the surface of the Earth by erecting a pole perpendicularly on the square so that it reaches the cloud. Why say that? Will?
Is he introducing the third dimension there? That you can do X, Y,
I
and
think
Z?
he's not really, but I guess somewhat to a degree, but not for the reason of exploring three-dimensional physics here. It's a one-dimensional issue that he's bringing up, like maybe a two-dimensional issue. But... How do we measure the locations of objects that aren't exactly where we are?
We take something else and put it like in between.
Yeah, you're
Measure
like,
something else that we know.
right? You're like, oh, he's there. Yep, Matt Dallas is right there. It's harder for you to do. It's actually kind of interesting. I'll let that go. Like, in order to find out where this remote is, I have to reach out and touch it. And then my knowledge of that is based on some other knowledge of what I think the length of my arm is and all these. Like, I need an object. I need to have a physical object to measure the position of something else. Otherwise, I'm just hypothesizing. And you're like, well, we can find the positions of stars or the size of asteroids by using the method of parallax, and we don't have to touch it. Or at least, astronomy people would say that. You might say something like that. You might say to yourself, like, I'm pretty sure the TV is like X number of meters away from me right now, and I'm not poking it with a stick. But aren't you? How do you see the television?
Light travel.
The light has to travel to you. Like, if you're seeing the wall on the other side of the room, trying to decide how far away it is, you have to strike it with objects, photons. They have to collide with it, and then they have to travel to you a finite time. And in that process, stuff can happen. Right? Relativity can be an issue. As soon as you have to look at something farther away, in order to know anything about it, information must be transmitted by physical objects. And that puts a limitation on our knowledge based on how quickly physical objects can move and how we measure their size. So that every single measurement you ever make is dependent on relativity. Sorry. Any questions or comments there? Fair enough. Moving on to page 32 of the digital document. I'm highlighting this section as the place where I think the highest percentage of my students in history have been like, I am done with you. We are not talking anymore. Purpose of mechanics is to describe how bodies change their position in space and time. That's pretty satisfying. You're like, yes, that is why I like physics. I should load my conscience with grave sins against the sacred spirit of lucidity. Okay, Einstein, come on. It's just You started out strong, buddy. Where are we going here? Formulate the aims and mechanics in this way, but without serious reflection and detailed explanations, let us proceed to disclose these sins. And then here's the sentence. It is not clear what is here to be understood by position and space. The position thing, I think you can buy. Like, yeah, what position is, I now authentically believe that that has issues. Where things are, how long things are, that is more confusing than I thought before I came into this digital room. But it is not clear what is to be meant by the word space. And I'll pose this question to you as being relevant to our eventual discussions of general relativity and quantum mechanics. What is space? She's either laughing at me or the question, maybe the bow tie, not sure which, but what is space?
The Aether thing that you talked about.
The what? Oh, right, the experiments of Michelson and Morley said, well, there isn't any.
Okay.
What is space? Eni?
Like an area or volume, like
Okay.
an expanse. Like
What was the
that's
last
like
one? An area or volume what?
that's like continuous.
Okay, a continuous area or volume. I would add the words maybe in our universe.
In our universe, sure.
Yeah. Well, then what makes space different than a table?
Like, isn't a table like part of space?
You tell me. Is a table a piece of space or does it occupy space? Sorry.
Space then,
Okay, go ahead.
So space would be the stuff in between stuff that takes up space.
Okay.
So
Are we saying
occupying, everything else is space that isn't currently occupying
The volume.
a volume.
The volumes that aren't occupied by matter.
Yes, are space.
the volumes that are? So are you saying that the volumes that are occupied by matter have no space?
They might have space between like atoms and stuff, you know. But, yeah.
But like, do you take up space, or is the space only between you and Kaylee?
I take up space, and there's also space between us.
Okay.
Wouldn't there not be space between you because they're like the molecules of air and all that?
Yeah. So I think what we're realizing is we're saying that space is like this overlying set of like three-dimensional Cartesian coordinate axes that have locations ascribed to them. And then objects exist in those locations or don't exist in those locations. Which is true until like 1925. And then even that's a problem. Because in quantum mechanics, space isn't continuous. Again, sorry. But do you guys think that space, and I'm going to be really philosophical here, and Jasmine was going with the hand motions. She was getting like right in there with the philosophy. Would you say that space is? Would you say that space itself exists and is a thing? Or is space nothing? By the way, this matters.
I mean, nothing can. No, never mind. I was gonna say like nothing can be, sort of like nothingness can exist. So I feel like
Nothingness can't exist depending on space existence.
Eni.
I'd say that space is nothing, kind of like the way like time. You can say time is nothing because like it doesn't actually. It's like our way of like measuring things. Like space is our like three-dimensional like coordinate plane. It doesn't actually exist, but it's what we use to measure like position and like the same way time like what like is how we measure like the space between events.
Uh-huh.
And
Okay.
it doesn't exist like in it's like a concept that we
It's
create.
a concept and not a thing. Jasmine?
I don't know, just because he brought up the whole thing about time being nothingness, it kind of brought up, like, some theories about, like, time kind of being related to entropy and the fact that we're moving in a forward direction, regardless of how you measure that forwardness. So I was thinking if maybe there's kind of like that's, like, sort of like time, if there's something like that for space, kind of related to entropy, you know, and, like, I don't know.
I hope you're all at least enjoying that this question is hard. Like, you did not expect this to be a hard question. So here's the thing. As a physics person, what physics quantity would you say a thing has that makes it real, that makes it exist? What's the quantity you would what's that? Like what is the thing that the physics concept we ascribe to objects to say that they exist?
Volume.
Volume is a measurement of distance, and you just said that measurements of distance were measurements of space, and that space doesn't exist.
Mass.
Mass is a form of, and we haven't done this yet, but you know it. Mass is a form of
Energy.
energy. If space had its own energy, then it'd be a thing. Very, very far down the line from here, guess what space has? It has its own energy. And space exists. Nothing is nothing. It's not even space. Nothing is totally inconceivable. That is why he's starting to hit this here, because eventually in general relativity, we have to allow space to change in shape. So I will just breathe, just let it go. Just changing the page. Going down to page 35. This is pretty quick, and much less existential. I just want to point out here, when he gets into the Galilean system coordinates, he comes right out of the gates with the law of inertia, otherwise known as which of Newton's laws?
First.
Newton's first law. I'm just pointing out very quickly, that's hugely important to relativity, especially when we get to our conversation about general relativity. The law of inertia turns out to be very well preserved, even as the laws get more and more complicated. That simple, elegant thing that objects not experiencing forces travel in straight lines remains true and is important. Skipping ahead again. To page 45. Where am I? Nope, I'm wrong. Yep, no, I'm right. 20. There we are. Okay, so in this chapter, he's talking about light propagating, and this is where we started our discussion. He said that propagation of light relative to the carriage comes out. He's talking about if de Sitter's assumptions were right. If the velocity of, you can see it right here. If the velocity of the emitter mattered to the velocity of light, we would see light slowed down or sped up or whatever. And what he says in this chapter, this is a big one, is that, well, one law of relativity says that the speed of light is the same in every reference frame. The other most inviolable law of the universe is that the laws of physics have to appear to be the same in all reference frames. But that the case of light trying to travel at the same speed gives us different measurements of length and time and all the weirdness that we've been talking about these past 2 weeks. Which seems to suggest that either the fact that the speed of light is constant in all reference frame must be wrong, because it's contrary to our experience, or the fact that laws of physics are preserved must be wrong in order to preserve our experience. But both of them are true. So what solution do we have? If we say that the distance between 2 points is a preserved number because of the laws of geometry, but that holding the other two things true, the speed of light being the same and the laws of physics being the same, makes that number change. How do we resolve that? Kaylee?
Space isn't exactly Euclidean.
You let go of geometry. And I bring this moment in this book up, because to me, this is Einstein's real genius. You guys all familiar with Johannes Kepler? What did he first propose? Yeah, Peter.
We talked about like orbits.
What about the orbits?
They occupy a constant area around the planet or something.
Yeah, that's just the equal area and equal times. That's the second law. The first law is the one that's so simple that people forget it. It's just the statement itself. Will?
Oh wait, no, never mind.
Yasmin?
Just that they're elliptical.
Just that the orbits are elliptical. Now, in my like super basic introductory physics class, I make a big deal of this in the history of science. Because the problem with that, there are religious implications, etc. But from the physical perspective, we look up into the sky, we see things going around us, and we think to ourselves, those need to be embedded in something, because otherwise, wouldn't they fall down and hit us? Right? Shouldn't that planet fall down and hit us? So shouldn't that be stuck in something so that it doesn't hit us? So shouldn't it be embedded in something? Oh, it's got to be clear. A giant crystal sphere. There's a huge crystal sphere around the Earth. Mercury's in it. And that sphere is spinning around us. And Kepler's like, that doesn't work. And many people are like, that doesn't work. Everything's too complicated. Epicycles, all kinds of craziness that Tycho Brahe sees in the patterns of the motions of the planets. And Kepler's like, you know what? If you call these elliptical, there's no problem. And the people around her are like, you're insane, because if they're elliptical, how do they keep from falling? That means, like, if they're going, the thing that's holding them has to change in shape and size. How would it know to do that? If it's attached to something rigid, it wouldn't change shape, so automatically the path should be circular. How could the planet not fall and hit us if the orbit's elliptical? You're crazy. And Kepler's like, I don't care why. I just know that this is the right answer, and I'm going to go with it and see if it works. And he shows that it does work. And by letting go of this convention that seems so obviously important, by saying it is not required, I do not need for the planet to be supported. Someone else can figure out the answer to that. That person's called Newton. He's not born yet, but whatever. Somebody else can figure out how the elliptical orbit works. I'm just going to say that it is elliptical. And Einstein is like, look, I'm going to let go of geometry. These things have to be true. Geometry's out the window because it's standing in the way of what is clearly correct. So it's gone. And that is bravery, and that is scientific genius. He, however, turned out to also be Newton and be able to explain the whole thing. You know what I mean? But this is a really important moment when he is willing to throw away what mathematicians and physicists hold most inviolate, the shapes of squares and triangles and circles and lengths and things like that. When he has the bravery to get rid of that, that's what makes Einstein Einstein. The last thing I want to bring up is farther along and might have freaked you out, and I want to just calm you down about it. If you got to it, I realize this is hard reading. I'm on page 39. I'm almost there. Einstein does something different from what I did. I did thought experiments, and we talked about length contraction and time dilation. Einstein comes up with something called the Lorentz transformations. Now, you can see gamma there, right? But that is not the length contraction equation, nor is it the time dilation equation. I mean, that time equation has x in it. The time equation has position in it. What are these? What they are is a way to convert, like if I say, Matt Dalis is 1 meter from me this way, 0 meters from me this way, and he's hunched over. So 0.1 meters that way, and it's at 323. This is a way for you to say, for Jordan to say, like, well, I see him as being at this position in X, this position in Y, this position in Z, and at this time. He would see it, even if Matt weren't moving, he would see a different time because the pulses of light coming from Matt would get to Jordan at a different time because they have to travel the distance X, and that's why X is in there. You can use these to derive the length contraction and time dilation equations. I think it's a lot more challenging. Some of you might have wished that I did this. Some of you might know about that. I'm not doing length contraction. I'm not doing the Lorentz transforms. They're very cool. They're very important. If you want to study physics very, very far, you should learn this way of thinking about relativity. I'm not going to use these equations for your test. We're going to be tested on length contraction and time dilation and relative velocity and the stuff that I've been teaching you in the videos. Okay, so if you read this and you see that it's different from what I've been talking about you about so far, with you about so far, know that it's important. It's cool. Don't worry about it for your eventual test. Do you understand what I'm saying? I just wanted you to have, not be freaked out by these very. All right. Any more questions about or comments about things that you had to read? And the obvious one, yes, it's translated German. It's hard. Jordan? Oh no, I thought you were raising your hand. You just got highlighted on my screen suddenly for no reason.
Oh.
Nothing. We will read a little bit more from this much later. I would say it's actually an easier chunk. There's no math in it, and he talks about a treasure chest held from a rope. But the other reading after that will be Feynman, which is a lot easier and a lot more fun. But I hope there was some satisfaction, that you found as lovers of physics of reading some of Einstein's words in English, and you can see some of the connections between what he had to say and what we've been talking about. Okay. I'm hoping for that first worksheet from you by by like midnight tonight for whatever your time zone is. Do your thing. And I've got more videos coming for you on momentum and energy and things like that. I just want to warn you, we're at. Any of you have Science Olympiad teams?
Yeah.
Yeah. We have an invitational tomorrow that's like a 13-hour day. I'm pretty sure everything will be up and ready for you tomorrow. If I'm late with videos tomorrow, I apologize deeply. Please let me know if it generates problems for you. I can adjust things, but they should be ready to go for tonight, so you can watch them tomorrow. But apologies. This week has been rough, and I was a little slow getting things up in a timely fashion to you, so I apologize there. Okay. Anything else I wanted to say?
Mr. Walker, on the attendance sheet, you combined my name and his name.
That's the last one.
Oh, he's editing the document I'm looking at right now. Oh, all right. I'm going to end with one thing that's that might be a little bit silly. I wonder if it might work. Who is the farthest west? Fort Worth, Canterbury. You're both in Texas, right?
We're in Indiana.
Yeah.
Oh, you're in Indiana. I'm sorry. Sorry. Fort Worth. You're probably farthest west.
Yeah.
Yeah.
Is there anyone from California?
I don't think so.
From Chadwick? Okay.
I want to try something weird. I'm gonna count to 3, and when I get to 3, I want everybody to, like, I don't know. Do you want to scream or you say the word boo? What do you want? It's like whatever. We can yell physics.
Let's scream.
Pick something.
Screaming is good.
What do you say?
What's that? Screaming? Just go ah. Okay.
Yes.
I'm gonna count to 3.
Okay.
Make sure your mutes are off. I'm gonna count to 3. When I say 3, just go ah. Okay. I'm gonna go 1, 2, and 3 ah. 1, 2, 3 ah. So
okay.
I'm not sure how this is networked, but I think there's a chance, and I bet it's not gonna work, but I think there's a chance that when we all scream ah, the people in Fort Worth are going to hear us say it at the same time, and the people and people at different locations will hear the as at different times because of relativity of position. Because it'll take the longest time to get to Fort Worth, but that could be completely wrong depending on how routers are set up, and like your network and all that. You know what I'm saying? All right. So Fort Worth, the pressure's on you.
Should we say 1, 2, 3?
No, I'm the farthest east, so I should
Okay.
say 1, 2, 3, and I'll tell you why. I'll tell you the experiment that this is based on at the beginning of next class because it's really funny and it involves frightened cows. All right. So
Wait, so are we all screaming or just Texas?
All of us are screaming.
no, all of us but
yeah.
Texas.
Oh, but
Okay. That would be so awesome if this works. All right, ready? And so it's 1, 2, 3, ah. Ready? 1, 2, 3, ah. Fort Worth. Was it at the same time?
It was off.
Anybody hear it at the same time?
Yeah, I think
I
I
did.
heard it at the same time.
Jordan, you heard it at the same time?
I'm pretty
Okay.
sure. Yeah.
I guess what's important is he heard it mostly at the same time. I heard them at wildly different times, which is kind of cool.
Ours were slightly
All right,
different times.
I'll tell you why I did that next time. See you guys later. Thank you for putting up with the reading.
Yeah.
Sending a signal out. You're hearing the